All right, so let's move on to another one, CO2, carbon dioxide. For this, it has one carbon, which brings 4 valence electrons, plus 2 oxygens, which bring 6 each. So this is a total of 16 valence electrons to assign. As is usually the case, the first atom is the central atom, and whatever's listed next in the formula is the outer atoms. To tether this together into a molecule, I used 4 electrons, and so I have 12 electrons to assign. And as the pattern that we always follow, we go 2, 4, 6, 8, 10, and 12. We assign the 12 electrons to the outer atoms, and that leaves me with no electrons left to assign. So I've used all my electrons, but the carbon here is not satisfied. It would like to have 8 electrons around it, and right now it's got 2, 4. And so what can happen is here, the oxygen on the left can take 2 of its pairs, and we can form now a triple bond to the central carbon. That leaves 1 pair on that left oxygen, and I didn't use any pairs from the right oxygen, and so there is, it still has the 3 pairs of electrons. And now all of these atoms are satisfied with respect to the octet rule. Instead, we also can do a structure that I call share and share alike. So each of the oxygens can donate 1 lone pair and form a double bond, and we can get the structure that has a double bond to both of the oxygen. Or it can be the right side oxygen that does all the heavy lifting. It donates 2 of its lone pairs and satisfies the carbon in that way. And so we have these 3 different structures here, and like if you watch the ozone, the O3 video, these are together, these 3 structures are a better representation than any one of the structures alone. But what we also can do is, when we have inequivalent structures, as we do here, this structures on the outside are equivalent to each other, but both of those are inequivalent to the structure in the middle, we can actually say which of the 3 is the better structure to describe the molecule if we had to do it with just one. And so I'm going to take and redraw the structure here on the left-hand side. And now I'm going to assign formal charges to the atoms. Okay, and so in the Lewis structure right here, the oxygen has 1, 2, 3, 4, 5. Okay, so in the Lewis, this one has 5. The carbon has 1, 2, 3, 4. And then this oxygen over here has 1, 2, 3, 4, 5, 6, 7. Well, from the periodic table, if we look, we expect an oxygen atom to have 6 electrons, and we expect a carbon atom to have 4 valence electrons, the isolated atom. And so this oxygen over here, we expect it to have 6, and it has 5. So this oxygen has a positive charge. The oxygen on the other side here, it has 7 electrons. We expect it to have 6, so it has a negative charge on it. And then the carbon, we expect 4, and it has 4, so there's no charge on that central carbon. This guy over here is going to be exactly the same, just flipped around, so I'm not going to worry with it. I'm going to look at the middle one here and see if we can decide if this middle one is better than the outside structures. And so I will redraw it. And divide it up. Okay, and now in this structure, as I've drawn it, there's 1, 2, 3, 4, 5, 6 electrons in this Lewis structure. There's 1, 2, 3, 4, 5, 6 electrons in the Lewis structure for that oxygen. And then for the carbon, 1, 2, 3, 4. Okay, and then again, these are from the Lewis structure. From the periodic table, we expect 6, 4, and 6. And so no charge on the oxygens and no charge on the carbon. Well, it ends up, this is one of the first rules that we'll talk about. If you have a choice between a structure that puts no charge on any of the atoms and a structure that does charge the atoms, then the structure that puts no charge or minimizes the amount of charge that it has is better than the structure that has charge in it.